Okay. So good afternoon, good morning, everyone. I hope you can hear me fine. Let me know if not. Okay, great. So first, thanks for the organizers for arranging this workshop and for giving me the opportunity to not talk about islands nor averaging. I might regret. But okay, I already, this is one thing that I'm not supposed to do in this talk. And the second thing that I'm not supposed to do in this talk is to actually pretend to give a Blackboard talk, which I might also regret as we go along. But in any case, life is to be lived. So this talk is going to be, as the title says, it's a study of gravitational perturbations of extreme Kerr. And most of the talk, the vast majority of the talk is basically a project for which the results are going to appear that involves Victor, Joan, Wei, and Boyang. And here I really want to highlight Boyang and Victor. They're, as the youngest members of this collaborations, they've been exceptional. All of the hard works and computations, it's all due to them. And Boyang, just so you know, he's applying for postdocs this year, so keep an eye. I'll also touch upon at the end, and it will come depending on how many questions I have and things. I'll mention it here and there, but I also wanted to highlight that this is also in a very similar flavor to another project that we have in relationship to 5D black holes that involves Juan, Chiara, and Evita. And Evita is here connected, I see. Now, because it's a Blackboard style talk, I won't be able to give references throughout nor do a big overview of what's happening. So I collected some list of references here, kind of my favorite. And the first one that I want to point out, because I will be talking about extremal and near extremal black holes that are rotating. This first one, which is written by Tarek, who's also here in the audience. It's one of my favorite papers on this. Hi, Tarek. And so I strongly recommend you to read it. I think it inspired me, and I think some of the future directions as we discuss, I think this paper is quite important. And also, actually, these last two papers are also pretty recent, and I think they also contain some interesting results and moving forward in this type of program. This one actually appeared just today. But there's many more references, and I just decided to highlight some of them that are the most kind of intimately connected from my biased perspective to the Kerr black hole. So, okay, so what are we going to do today in this next 40 minutes or so, or however long Shira lets me talk? So what has been central and obvious in this conference is that JT gravity, and I think, yeah, you can see what I'm writing, has been central in understanding quantum and holographic properties of black holes, or to be more precise, of near extremal black holes. Okay. And the main message of this talk, and the question that we're trying to understand, is basically where does this beautiful JT description sit if you are in the context, if you were like a relativist in the 70s, basically. So where does JT sit in the context of gravitational perturbations? In particular, because of the title of Kerr, which is a really well studied subject, and also a very relevant one nowadays because of the new astrophysical developments and observations of black holes. And so that's the basic aim. Okay, so if you wanted to talk to a relativist and explain to them where is this JT, this Schwarzschild mode, in their language, in their context, this is kind of like the set of tools and sort of highlighting, okay, this is where this thing is sitting. Okay, and so there's two things that I want to highlight in this process. So one question that we have, and I'm going to mention it in the discussion because This is one of the ones that is most challenging. I do have something to say, but I'm going to favor some other aspects. So one is basically of the near horizon effects on the UV. So basically this JT description is very well suited for the near horizon part of the geometry. And so one of the things that we've been trying to understand is the gluing of how this dynamics in the near horizon gets sort of translated to the far region. And the other thing that is more important that I hope I do make a clear point here is that new features appear due to rotation. Okay, and I think this is important, and that's why I was highlighting that first reference here, because there's an interesting sort of direction in terms of the holographic description of these new descriptions, of these new features, that from my point of view, it's a little bit like doing chemistry, okay? So you can take the point of view of this program as basically something that I'll denote black hole chemistry. Okay, so we know what are some basic building blocks. We know some of the dynamics, and now you kind of want to build sort of universality classes if you want, based on these new features that rotations and charges and other parameters will bring into the picture. Now, I'm not going to, since I think everybody here in the audience is very well acquainted with many aspects of JT gravity, but please, if something is not clear, let me know. There's just basically two things that I'm going to be referring to and sort of using about JT gravity. So just two basic aspects that I want you to remember about JT and near extremal black holes. So the first, so number one, number two. So the first one is just, well, the song and dance that we all know is that the role of JT is that if you start with a geometry that is ADS2, there's a notion in which it brings it to something that is nearly ADS2, and the basic effect here, so this has very nice implications, but the only thing that I want you to sort of maybe keep in mind is that one of the effects that we quantify in this context is that if you start with some extremal entropy, some Bekenstein-Hawking entropy, at extremality, this JT sector basically describes the deviation away from extremality by a linear response in the temperature, okay? So that's one of the things that, that has been observed. And the second one is just, this will be mostly nomenclature and just a quick reminder. I will write this field capital Phi. This will be what I will call the JT field. So basically in the context of JT gravity, this is just this action like this. And there's only three things very quickly that I want you to remember about this friend here. So the three things is that what is its equations of motions, basically the stress tensor vanishing, B. Plus GAB phi equal to 0. In language of ADS2, this is an operator of conformal dimension equal to 2. And from the point of view of black holes and how we think about them, what this field is from a higher dimensional point of view, it will be useful in many parts to recall that this phi is just basically the size of the sphere, which is a very, very accurate sort of analogy. For instance, if you're doing the Rice-Ostrom black hole, okay? So that's basically the role. And because it's the size of the sphere, it's kind of then, so from this point of view, is sort of then, so if you can guess why, like it changes the area of the horizon, and that's why it's accounting for the entropy away from extreme, okay? And I'm very kind of, I'm glossing through various details, but that's what I want you to remember about JT gravity, okay? Very good, but we want to answer this. We want to know where does this nice aspects and nice description fit inside of the extreme Kerr solution. Okay, so because the Kerr metric is kind of annoying to write in real time. I wrote it before, so now it's slow. Okay, there we go. It's scrolled up. So here's the Kerr solution in 4 dimensions. So the typical thing that you study in a GR class. I'm not doing anything more fancy than that. So as we all know, yeah, this is how the metric looks. There's some the functions of R and theta that I'm not going to write down because it's not super important. But what you maybe want to keep in mind is that there's a blackening factor. The extremal limit is defined when m is equal to a, and I'll call that parameter m naught. This geometry has a near horizon limit called neck. So neck. So there's a beautiful paper by Bardeen and Horowitz on this. And it's basically, so when you're at the extremal limit, there's a decoupling limit that you can take of the coordinates. And so if you start here, you can implement this decoupling limit and get to this geometry that I wrote down below. And in this geometry, the things that all extremal black holes share is that there's an ADS2 factor sitting here, and there's a fiber that's in this other direction. So the fact that it's rotating is because you have that term like so. Okay, so this is the solution that we'll be studying, and this is the near horizon geometry of that solution. Very good. So, great. So we want to study gravitational perturbations with our hat from the 70s and sort of understand where is this new development of JT in this language. Okay, so let's start studying gravitational perturbations. And here I could spend the whole talk just reviewing what has been done, but I won't. But some of the key authors and the results that I'll be stating is basically based on Tolkowski, who was using the Newman-Penrose formalism to describe the linearized perturbations, gravitational perturbations. There's a nice theorem also in the 70s by Wald, but then I don't know, there's your favorite, you can open, for instance, Chandrasekhar book or something like that. Like there's tons of different approaches and stuff, but Tolkowski will be the closest that I'll be using, okay? So for today, because I don't have infinite time, I'll focus on neck, okay? So we'll discuss in detail the gravitational perturbations in this near horizon portion. Also because it's not going to be important for JT itself, I'm also going to focus on perturbations that are independent of the angle phi, okay, of that killing direction. And in the language of Tolkowski, what you would do, you would say, okay, the best way to describe this gravitational perturbations is to focus on what's called the Weyl scalars. Weyl scalars. Okay, so in 4 dimensions, the Weyl scalar has 10 independent components, which you can gather in 5 complex variables. And you only have to actually focus on 2 of them that are called phi 0 and phi 4. Which are basically contractions of the, sorry, this one is L alpha and beta. So you define 4 null tetrads that are these L, M's, and N's that I'll write in a second. The details are not important, but just if you're familiar with this, so you know what is my context. So M is a complex null vector, so M bar is a complex conjugate of it. And so these are the variables that you use in the Tolkowski formalism to describe the gravitational perturbations, the for spin 2 massless graviton. And the nice thing about those results back in the day is that there's 2 very nice features of these perturbations. And the first one is that basically at linear order, these things are invariant under, so if you rotate the tetrads, it doesn't matter, like at linear order, psi 0 and psi 4 doesn't change. So at linear order, they're invariant under tetrad rotations. And they're also invariant under diffeomorphism, so they're also gauge invariant. So that's super nice. And then in this Neumann-Penrose formalism, so what Tolkowski did was that you have some set of first order linear equations for these variables, and he basically managed to decouple them and showed how only psi 0 and psi 4 obeyed a master equation. So there's this Tolkowski master equation, which I'm also not going to write, but it's basically a Klein-Gordon-like equation for the spin 2 degrees of freedom. And he also showed that it was a separable equation. So, so you can separate it in terms of the angular and the radial part. Okay. So this is the way, well, it's my favorite way of understanding gravitational perturbations. Okay. Now, in this language, what are the possible types of things that you can have? So the possible type of perturbations. So if you read any of these papers, old or new, change the color so I don't get bored. Okay, so there's of course gravitational waves, which I'll show you in a moment how they appear. You can also describe changes of mass or angular momentum. There's diffeomorphisms, which are the most boring things because these guys want to get rid of them. And you can also have changes in the knot charge or acceleration parameters and stuff like that. But the bottom line is that, for instance, if you look at these papers, the main emphasis is on this first sector, where both psi 4 and psi 0 are different from 0. They're actually not independent. So if you just solve for one, you'll get the other one. So you usually just focus on one of the Weyl scalars and then you get the other. Well, it says that it's the same equation, just with s equal to +2 or -2. And these two types of perturbations, so on Kerr, so on the full Kerr background, these perturbations will lead to trivial Weyl scalars. And so this is what Wold showed in the 70s. Okay, so a change of mass or a diffeomorphism does not induce at the linear order at non-trivial Weyl scalar. Okay, now, but what we're going to do, because we want to build this intuition of what the JT mode is doing as like something that is changing some size in the geometry. So what we're going to do is we're going to grab this line element here. And I'm going to paste it. So we're going to basically write a perturbation in this geometry, and I'll relate it to this Weyl scalars in a moment. So let's consider the following modification to this line element. So I'll add a perturbation where I'm changing things here. So they're in light blue. I'm making those two changes, and then I'm going to add, for consistency of the ansatz, you also need to add a term there. Okay, so let's consider a modification to the neck geometry of that form. And so this chi is going to be a function of the positions of ADS2 and the angles. So this here, just to emphasize, this is the ADS2 coordinates. And so this is going to be the main thing that describes the linear modes. So although I wrote it, I wrote it down here in the denominator, but it's just for clarity of like how I'm modifying the ansatz, but everything is treated at the linear order. So you would expand, but I don't want to write it in the expanded form. And this connection A is actually, which also will depend on the ADS2 coordinates and the angle theta. It's not really like, so for consistency of this ansatz, this is just a function of chi, okay? So I'm just writing it for completeness so you know like exactly how the metric is modified, but the degree of freedom is just going to be this function, chi. So how are these things related to the Weyl scalars? So you can just compute the Weyl tensor for this background. So let's write it down. It's actually not that complicated. And then psi 4. Goes like this, and these vectors, and they're null on ADS2, they're null vectors on ADS2, and they multiply to -1. Okay, but this is the relationship between writing the perturbations as I'm writing them here, in contrast of using this Weyl scalars. And of course, this guy, I'm going to treat it, so chi is going to be like a scalar mode. And it's not surprising that it, by acting with two derivatives, is related to the spin 2 degree of freedom. Okay, so very good. So let's see what, so now we have to impose equations of motions. So this linearized perturbations obey equations of motion. So let's start digesting what do you get. So the linear, okay, so what you would do, very similar to how Tilkowski did it, I think. Okay, so so because of the sine square that is showing up there, and to make connection with what happening before, so let's just write down this mode decomposition like this, and I'll go through this quickly. So this one here, it's basically just a spheroidal or harmonic. It will become in a second Alejandra polynomial. But this guy over here, so I separated the angular and the ADS2 coordinates. And the ADS2 part, for which I have the subindex k, it obeys a Klein-Gordon equation with eigenvalue k. Okay. And in terms of, if you ask me, what is the conformal dimension of that field? So it's just the usual one. So, well, you will have plus minus 1/2 plus minus quarter plus k. Okay. And there will be a BF bound that for k has to be bigger than -1. Okay, very good. So that's what the Einstein's equations tell you. If you have an ansatz like this, these are the modes. Okay, so now let's look at what you would call the gravitational wave sector. So in the old literature, the number one thing that you would do as you're doing this analysis, it kind of comes at order 0. It's even basically implied, is that these functions here, these angular functions, have to satisfy a good Stern-Liouville problem. So you want these things to be normalizable. Okay, so you want them to have a well-defined inner product. You want them to have finite support on the sphere. And so that will tell you that basically, let me stop writing with blue. So SK are associated Legendre functions. And in the notation that I was using above, this K is L times L plus 1, and L starts at 2. And it's an integer. Okay. So in terms of this conformal dimension, which will be L plus 1, is always bigger or equal than 3. That's it. Okay. So
there's a question in the chat. Someone is asking if the configuration is still time independent.
No, it depends. So XA is it's a label for the T and R part of the ADA. So when I use this index XA, it means that it can depend on T or R. So this is a function of T and R. So I just didn't do the Fourier decomposition in time. You don't have to at this. No, there's no need. So this is the Klein-Gordon operator on ADS2 that has time derivatives and radial derivatives. Okay, so those are the gravitational waves. They will look like operators in this notation using this parametrization in terms of chi. There will be irrelevant operators with conformal dimension bigger or equal to 3. Okay, but then you're like, but Alejandra, but we want a delta equal to 2. Why don't you put delta equal to 2? Okay, we'll put delta equal to 2. Okay, so if you take k equal 2, then you'll get delta equal to 2. And why do we want delta equal to 2? Because that's how that smelled like, it looks like the JT thingy, right? It looks like the JT thing. Okay, so this is what we'll start calling, in a very loose way, the JT sector, but it's only like the first half, which I hope I'll get to the second half, I promise. So this will go quickly. So of course, in this case, what happens, so you get that the equation satisfies blocks of K2 equal to 2 times K2. But then you will say, why did Mr. Tolkowski hated the solution? Well, the reason why he hated the solution is because then if you solve for the spheroidal harmonic in this, for this lovely field, so you get two constants, two linearly independent solutions, that just because they're short, why I'm writing them explicitly, but just so you can appreciate. So the reason why a relativist would have discarded this is because this thing has poles at theta equal to 0 or pi. Okay, so you can avoid one of the poles, but you can't avoid both. Okay, so they're not as expected because all the other ones form a complete basis of smooth function on the sphere. If you pick a different value of k, you're going to get something that is not single valued on the sphere, or will have this one's are single value. You will get like a singularity or some other problem in the function, and that's reflected in this like lovely 1 over sine squared. And so, of course, then what you want to do is say, please get rid of this because this looks like a very pathological perturbation. And so you go back and you look at your Weyl scalars. And okay, so one easy way. So what I'm doing here, so let's put here the chi2, and then there will be an S2 of theta. And sorry, and the sine squared is also, because I had sine squared multiplying this thing. So these are the Weyl scalars. And so, okay, of course, an easy way out here will be just set chi2 equal to 0, and then we move along with the rest of our sector. But in this language, if you decided to just say, look, just set these conditions, sorry, with including the these derivatives. So if you say each of these terms is 0, in addition to this equation here, so this plus these set of equations, actually you can check. It might, since I'm not writing things explicitly in coordinates, but demanding 1 plus 2 are basically the JT equations of motions that I wrote at the beginning. Okay. So that's an interesting solution to the problem of like, let's try to get rid of these bioscalars because they look like they were having a singularity at theta equals to 0 or pi. Now, let me just remark a few things because it's very important in the, so some notes on this. So first, the first thing I want to say, so this level looks super nice. So I would be kind of, so this makes me happy. But it's not quite the end because there's still more to digest about what we're doing. So the first thing to observe is that this condition 1 plus 2 does not imply, so, and you can check this explicitly, does not imply that chi is a diff. So when I was characterizing the perturbations and I told you can either have gravitational waves or changes of mass or diffeomorphisms or this nut charge, inside of NEC, if you set the bioscalars equal to 0, it does not imply that it's either a diff or a change of mass. And so this chi thing, even though the bioscalars are trivial, it's not leading, like you can't just interpret it as a diffeomorphism. Okay, it will contribute to the change of mass, but of course the JT field does more than that. Now, the other thing to observe, so let me, sorry, I'll copy, since I want to copy again this equation, so you can stare at it and I don't have to go back and forth. So in this equation here, there's two other things that maybe someone could have raised their hand and been like, well, K is satisfying the equation of motion, but K is not controlling the size of the S2. So you're definitely not done. So even if you like thought that this was the end of the talk, which, okay, I know I'm close to the end, but it's not quite the end. Chi is not really changing the size of the sphere, so like intuitively from here, you're not going to change the entropy of the area of the horizon by this piece there. And the third problem that you can notice is that although the bioscalars, I made them trivial to try to avoid any pathologies, the geometry still has a conical singularity. So this is just to indicate that you're not done even after doing this analysis. It just gives more fuel for the relativists to not like this solution. So if you expand, so what I'm doing here is expanding near theta equal to 0, just so that it's more clear that you have a defect. So the geometry, so the dots are basically things that you ignore. So the fact that these two things have different sizes, this is what indicates to you that there's a singularity. Okay. So we're halfway. Why are we halfway? Because the thing that one way how to think about the next step is that we need to fix the fact that we have this pathology. So let's do that. So the second half, and I can't spell anymore, of course, second half of JT. So on the second half, so let's copy again the metric. I'll delete the chi one. So now let's, in a sense, let's reconsider this problem again. And let me do it in the following way. So now let me put an ansatz for how the metric should be perturbed in such that it's explicit that I'm changing the size of the sphere. And so the thing that you could do is add here a term like this. So this will clearly change the size of the sphere. And then for consistency of this ansatz, then, so there was a minus sign here. You also have to modify the line, the GTT part. So I'm writing it small because it's not going to be too important. And then you also still need a cross term there, but now this guy will only depend on phi. So these two things are going along for the ride so that they look nice. But the important part here is that I'm adding now this linear term that is clearly changing the size of the S2. Now, if we would have started the discussion, I'm sorry, and this phi now it's only going to depend on the ADS2 coordinates, and it's the size of a deformation. It's controlling the size of the S2. This thing, you can actually, if you wanted your metric to look like this, you can actually do it by a diffeomorphism. So a non-single value diffeomorphism that will change the size of the sphere exactly in this way. And so from this point of view, so you can induce this via a diffeo. It's a pretty funky one, so it's not one that you would have naturally thought about, but it's one that is linear with the angle phi. So that's why it's kind of like eek. We tend to not do diffeomorphisms of that form. But that line element above, basically you will be able to generate it by a diffeomorphism like this, and then there's another piece here that looks like that. Okay, and phi here, so as you build this diffeomorphism, phi obeys JT because you basically want the resulting metric to not depend on phi. So you start with a diffeomorphism that is changing the size of the sphere. So that's basically, you get first this term here. So that basically tells you, okay, you have to change the G phi by some amount so that it gets bigger. But then if you only do that, then it will introduce basically, introduce terms in the metric that are not single valued. And to start getting rid of those, you start noticing that the parts of the diffeomorphism that depend on T and R will start obeying the JT equations, okay? So this guy also obeys the JT equation. And it's the other half to our problem, because now if we go back to this problem of the conical singularity that we had up here, so let's return to our issue.
Alejandra, just your 5-minute warning. You actually started a bit late, but really 5 minutes.
Yeah, I'm almost done. The diffeomorphism is the last thing in detail that I wanted to show, and then it will be some blah, blah, blah. Okay. Okay, and so if you include the phi field, the way that this equation, so now I'm including, include both chi and phi into the discussion, and the only thing that happens, for instance, at the level of oh, how does your cone now look like? It looks like this. And from here, the thing that now I can delete this word singular, because now you can just say, voila, just set chi equal to phi, and you're not going to get a singularity on this sphere, which is great, because nobody likes cones. Okay. So to summarize, so that I try to pretend that I'm going to keep within the 5 minutes, but Shira told me to keep it wet. So the thing that I want you to take home here is that the JT sector in Kerr is basically composed by two different effects. Okay, so it's not so there's one effect regarding this non-single valued diff that phi was generating for us. And the other effect is that there's a mode which was coming from these Weyl scalars with k equal to 2 that we were calling, well, I'm not writing the subscript anymore, but okay. That it was this field chi. Okay, so these are the two sort of combined things that you have to analyze in order to get the JT sector, where this guy over here, just to emphasize, is basically controlling the size of the sphere. And this thing over here was a dynamical mode that got frozen, although it's not a diff. And the combination of these two effects, it's what you need in order to have a consistent picture of where this mode is sitting in a way that it doesn't induce singularities in the geometry. If you were doing a similar analysis in Weiss and Ostrom, it will not look like this. Okay. Now, another observation to make, the last one, I promise, and then I'll move to the conclusions, because you might now then ask about what happens to various observables. And this is why sometimes you might neglect or forget one of these two modes. So if the only thing that you cared about was the entropy and trying to describe the JT mode by basically understanding how the entropy of the system dominated, actually phi, again, just because it's the size of the sphere, is dominating the Wittgenstein-Hawking part. And also if you compute the free energy in a way where you neglect, well, no, if you just compute the free energy of the system, it's also governed by phi. Like chi is really not contributing to the free energy, which I don't quite understand why, because then if you compute, so just to confuse you, if you compute Iyer-Wald charges on this background, which you might think it's a more robust thing to do, instead of trying to compute on shell actions. So when you compute the Iyer-Wald charges, both actually, well, both are important because otherwise I don't know where to evaluate the two form if I have a conical singularity. But both of them contribute to the charge associated to dt, so that how much the mass gets augmented. So it's not, if you just looked at one of them and even ignore the cone, well, it's just ambiguous, and so I don't know what to do. But this, the contribution of both of them is what gives you this quadratic response with the temperature. Okay, so those are just some thoughts. Very good, so we're done. So I wrote down the conclusions because I was assuming that I was going to be running out of time. So here are some thoughts because as I suspected, I wasn't going to have much time to talk about the gluing. And so then how do we basically understand this mode if you're far away? So, so if you ask this question in the Rice and Ostrom black hole, there's not much to say because there's this very well-known theorem called Birkhoff's theorem. So they're not great, like yeah. And so if you glue the Schwarzschild mode in the near horizon to the outside, not very surprisingly, because there's nothing else that you could have done, the JT field viewed from the point of view of the outside geometry is just a diffeomorphism combined with a change of mass. And you can see that explicitly. For Kerr, if we are in the sector where phi is equal to chi, that's also true. It's way more messy because the metric of Kerr is messier, but Boyang and Victor did construct the diffeomorphism, and it's there. The thing that lingers, and that's why this paper is still to appear, is that there is a sense in which we can talk about these modes independently. And this one is coming from a contribution from a bioscaler. We've been trying to understand how to basically glue and interpret each of these modes without sort of like having this matching condition on them. And that has provided to be a bit controversial and subtle for reasons that if you want, I can answer, but okay. Then I did wanted to mention this 5D black hole. So this gluing process and then going beyond the linear level, it's going to be quite complicated in Kerr. And so we need a little bit more experience and courage as we move along. And this is where this 5D black hole is really nice because it's like BTC is another example of a rotating black hole, but it's too trivial. Like it really has like zero structure. Kerr is way too difficult. And this 5D black hole is like in a really nice, sweet spot in the middle. And then here I just wrote some other things related to things that I consider are quite important in this area in terms of this chemistry. One is not just discussing the area law. There's the Wald entropy. And so this basically, where's this JT sector if you have a theory with higher derivatives? And I think this fact that we describe it as a non-single value diffeomorphism for rotating black holes assures to you that you will always have the Schwarzschild mode no matter what. And this this JT type field, so as described as a diff, as a large diff, it will make it clear. Then yeah, I could rant about log corrections and about superradiance, but I'll leave it there because now I'm super over time. Okay.
All right, thanks a lot. I'm gonna, I'm not so sure how to unmute everyone, but let's see. But okay, so thanks. And let's see. So Tom Hartman has a question. Sorry. Yeah.
Hi, thanks. Hi, Alejandra. So maybe I said this, or sorry, maybe you said this, but I missed it. One perturbation of Kerr, of extreme Kerr, that we'd like to probably include in an effective field theory is the near extremal, is the one that allows you to go to near extremal Kerr. Is that perturbation allowed by your ansatz?
Well, that's the effect of this JT, like you mean the perturbation that will increase the mass?
Right. The one you would get, that's the same as that perturbation?
That's exactly what this one is doing. So from the point of view of the decoupling limit, because you can take the near extremal limit by adjusting the decoupling limit, right?
Yeah. So I thought it would have different asymptotics than...
What's that?
I thought it would have different asymptotics than the mode that you wrote, but maybe I'm just wrong.
No. So that's how we guessed a lot of these deformations.
Okay, so it does allow that excitation.
Yeah. So okay. If you ask me like, how did you come about like writing the thing in this? Sorry, let me like in this way. Well, it also includes the phi. This is based on what I expected from the deviations away, like from the near extreme.
Okay. Okay, thanks.
Yeah. With the phi field also include. So yeah, and this is also when we look at the IO wall charges and stuff like that, you're increasing the mass of the system. Like the thing is doing exactly what you expected in the JT.
Okay. Yeah.
Anemic, you should be able to unmute.
Hi, Alejandra. I just wanted to ask you a question regarding one of your comments towards the end. You did mention that BTZ is kind of trivial, which I guess agree. But it is also true that if you want to learn something from a CFT perspective, it's more useful. So I was just wondering if I repeat what you did, like if I take an extremal BTZ and like do this kind of perturbations, do you have some comments on what does it correspond from the point of view of an extremal CFT, 2D CFT?
Oof, no, from the point of view of the CFT, well, there's, right, maybe you were one of the authors in that paper with Henry and Joaquin?
Yeah.
Yeah, okay, so I was going to say that's our understanding of the CFT.
Yeah.
No, so the thing that, okay, so from this perspective, so let's say that I put myself in this mindset for BTC. So first of all, there's no graviton, so there's no Weyl scalars, they're all trivial. So from that point of view, there's nothing happening. That's also reflected, so you don't have, so when you have rotating black holes in higher dimension, and this we have seen happening in Kerr and the 5D cases, is that there's another mode representing squashing of the sphere, so you can enhance like some of like the overall size, but you can also like stretch it in other directions. And this is what this chi field is doing. And the BTC doesn't have that. So there's no other like, so there's only just the size of the S1 in the BTC, and that's why I was calling it boring. But let me just, one thing. In the BTC, because it's a rotating black hole, you can also induce the JT field. Sorry, yeah, now you're seeing. Okay, so you can see it also from here. So you can also do a diffeomorphism on BTC that is linear in phi. And that will give you the right physics.
I see. Yeah, but
you don't have to derive it from the equations, the Einstein's equations necessarily. Yeah. Which is also to not be too surprised because there's no graviton in 3D.
Okay. Okay, thanks.
Hi. Yeah. Hi, thank you for your interesting talk. I was just wondering if you have further comments on superradiance, because I was wondering how one sees the existence of ergo region in this context, because when you glue, you need to see the fact that the killing vector is becoming space-like. How do we see it in this context?
Excellent question to be answered. So that's it was one of my motivations to start doing this. I don't have anything yet to say. I am hoping that in this example, I'll be able to say something more substantial. In Kerr, we still don't have.
Okay.
Because it's really interesting. Yeah, because also the ergosphere, well, it depends on the black hole. Sometimes the ergosphere is inside of the near horizon geometry, but in this, sometimes it also sits outside. And so you might think that because you're deforming the theory, you're starting to like touch the ergo region. And so, yeah, so what will be the effect from the point of view of couplings or interactions that tell you that you're changing the from something being time-like to being space-like and so forth. So I don't know, but that's why I think this is why the chemistry of these black holes is quite interesting, because there should be different features depending if the black hole is charged or if it's rotating, or the interplay between the two.
Yeah. Okay, thank you.
So actually, I have a small question. I was wondering if there is some dual quantum mechanical interpretation of this, of the scalar chi in the system.
For Kerr?
Yes. Well, for the ADS2, yeah.
Well, here they're kind of matching. So I would have said the collective. Well, okay, yeah. The collective, the two of them is just the JT field. In this case, this chi does have, although, yeah, it has two pieces. It has a piece, an inhomogeneous piece that behaves in the very similar way as this one. But then the homogeneous piece of this mode, it's a more irrelevant operator. It has conformal dimension, if I remember correctly, between 2 and 3. Or no, maybe it could go even a bit above 3. Okay, I would have to look up the paper. But I can tell you what are the conformal dimensions of these guys. That's easy. Now, the thing that we're trying to understand here is understanding better what these couplings are and have some nice description of this in terms of SYK. So even in the first in this Maldacena Stanford Young paper, in one of the appendix, they describe like sort of, there's a note like, oh, the dilaton can couple to matter, and that's what happens in these models. And then there's some SYK interpretation of what the couplings are. So, but yeah, it's a bit, these systems are pretty, like, there's lots of terms that show up. So that's why it takes a little while to like, or at least I'm slow.
Well, yeah, that's very interesting. Thanks a lot for the beautiful talk. And I think we will move to the discussion session.